Okay, so the next talk is by François Mignard, and the title is Pixellisation of the Sphere.
The title is like that, obviously.
Sphere pixelization.
But if you see, obviously, the first slides, is I need to bring more precision about what I'm talking about. It's sphere pixelization for astronomy, not for football. But the picture here just illustrates the fact in the talk we talk about polyhedron and the projection of polyhedron sphere. This is what it is. So why I come to this topic with Michel? So a little bit of history for that. The object of the talk is the following. So I asked Michel one day, for practical reason, I will come back to that just later, is it possible to make a tessellation of the sphere, so tiling a sphere, with regular, uniformly same shape, same size tiles? So it's not a new problem, obviously. People have asked this kind of question for centuries, not question. So why? This is why I asked him. It was an idea to handle efficiently big astronomical data in the computer, just to arrange, to sort in such a way that in a memory or in the way to address a star position. I mean, two stars which are in the vicinity, close by in the sky are in some sense close by in the computer, which I will show is not what we do normally. So one need for that, in addition, a recursive system allowing to have a system able to accommodate 100 stars, thousands, million, billion stars. So it's not exactly the same, but we would like to have just a close-up having the same shape, the same kind of structure locally with more and more cells, essentially. So where did it start, actually? In 2002, from a question I asked for Michel while I was thinking about Gaia. So, you know, Gaia is a European astrometry mission will be launched this month, which is essentially dedicated to map more than 1 billion objects over the sky. So at that time, I was thinking, okay, we would need some point nice structure to store and search data on computer. So I say, okay, since I like polyhedron, I like this kind, it was not new for me, so that could be a solution. So I say it's an old age problem which has been tackled for many years. So one solution could be that, obviously. If you limit the number of structures to 20, the icosahedron projection sphere provide exactly the kind of cell you want. But obviously, you want something much and much smaller, definitely inside that. Looking on the internet, I found this one recently. It is focused or not? Yes. Which is very nice, but if you click in the detail, I mean, there are two kinds of symmetry there. Some are hexagonal, the main of them, but some are pentagonal. So it's not an answer to me because the cells are not the same shape. And then you have this one I discovered again on the internet. I've not looked in detail, which looks very promising. I mean, it's a way of tessellating the sphere with regular shape, but that does not offer for a recursive system. In that sense, you can divide up further this structure into smaller, which would have exactly the same shape. So this one is interesting. And again, you have, in general, hexagonal symmetry, but sometimes, this one, for example, the blue one is pentagonal. It's unavoidable in some sense. Even our solution will have this kind of defect because it's impossible. So this is the object. What is the problem we have in astronomy? Why I was interested by this structure. So astronomers have handled very large database of stars for years, even centuries. I mean, late 19th century, you had already cataloged with more than 100,000 stars, so they've handled that by hand to print in a book. So just to organize that in the book, so they decide to put zone around stars instead of having a full organization on a single line. But basically, what you have something like that in the sky with many, many objects. It could be very faint. And then you organize essentially something in the catalog, a long list of numbers. So if you just use the topology in some sense of the segment, or a circle minus a point, because it is what longitude is all about, I mean, they order the star on different parts of the sky with longitude, right ascension, whatever else. It means two stars which are two successive lines. One could be there, the other one could be there. So it's very impractical in practice. So I would have liked to have something which maintained more or less this notion of vicinity with the mapping. So this is what I asked Michel for Gaia. So essentially it's fair tiling, not a new problem for astronomer, mathematician, always useful, still used for telecommunication organization, how to put your antenna, your relay at the right place so that you minimize the number of relay. So maintaining the optimal distances. It is still known in mathematics literature as a Thames problem. So you can look at the marvelous book of Marcel Béger, L'échelle de Jacob, in which there is a full chapter about this issue of tiling regular sphere. So unlike the plane, there is no natural, no single and simple solution. A plane you can tessellate with many kind of tiles, like the square one is the simple one, which answer exactly the question. So the system must possess, I said before, some hierarchical features so that we can arrange it for larger and larger number of objects. So we have in nature, if you look at nature, has sometimes need to organize itself in more or less regularly distributed directions. So let's see a few pictures I took myself. I'm like botany, so I do many pictures. This one is the ivy, so the lierre, helix, which is not a full sphere, but essentially what you see in nature as arranges those small stems to be more or less at the same distance from each other. The distance to the nearest neighbor is always the same for all of them. And then when the buds are open, I mean, you can see even some tiling of something which approximates a sphere. Obviously, there are irregularities in that. It cannot be irregular, fully irregular at that level. But it's one of the solutions. And then when you have the fruit, it looks like the sphere packing on a sphere. The optimal way of putting the more possible sphere with the same surface, same thing. So it's approximate solution. And then the last one I have, which is a papyrus of Tracopon perifolius, or salsify. Again, all these small seeds, which are at the top, are more or less regularly distributed. So we have some approximate solutions, which are not easy to transform into mathematical aspect because they are not fully regular. But the principle is there. What astronomers are using, I've been using for long, is the natural extension of the icosahedron or octahedron, which is a hierarchical triangular mesh, essentially the geodome. So you start from a regular polyhedron and you project that. Now we use ILPIX for different reasons, and it has been essentially used for WMAP or Planck, for example. So the main idea in HTM is to divide a sphere into spherical triangular regions. So you need to start from the skeleton. The skeleton is either the octahedron, for HTM is octahedron actually, but it could be as well the icosahedron with 20 faces, octahedron being, I mean, this is the octahedron here. And then from that, you divide it on a plane. One of the triangle which is projected by central projection sphere into regular triangle. So it's amenable, obviously, to hierarchical definition. But when you project the triangle here, obviously the edges project exactly on the edges here. There's the vortices, sorry, here, and the edges project along the great circle line. But it's no longer true for all these intermediate lines of the planar triangle which project in some way. So you can see here, you start here with number 4. You have 4 internal triangle, and then we go here with the icosahedron, and then we benefit from this hierarchical system. But the line inside there, the blue line, are no longer great circle projection, are just central projection of a planar triangle. So they look like more or less similar, but they are not fully similar. But obviously you can go far and far and having something which is, so it's like a geodome. It's a good approximation. I mean, you have curvilinear spherical triangle. They are not fully identical. They have not the full symmetry of the group of the octahedron of the group of the icosahedron, but practically it's a good solution. And then a large one, and then I think I put for the beauty, no, not yet. So this is a nice recursive solution, obviously. Relatively easy to implement. So when you know it, it's easy. When you start, it's not so easy. Naming and locating each triangle with some number, with base 4 and so on, it's also quite easy and very easy to, very practical to handle. Each face has the same symmetry, the face, because as a triangle, but not so easy to handle as a rectangular or quadrangular mesh. But anyway, the spherical triangles is my main default, I consider, to HTM, have not the same area. So that's a big inconvenience. When you want to replace discrete sum by integral, I mean, you have to take into account the fact the surface of each triangle is not equal. When you want to determine density or plot density of something which is given in this triangle, I mean, you have to go into the surface of each triangle to correct the density. So it's not, the factor could be a factor 2. It's not negligible. So it's not perfectly. Okay, aesthetically, obviously, it would be much better if you could have equal area projection, maintaining more or less the shape, but having the same area. So, basic idea we have with Michel, when I went to him for that, said, okay, say Gaia would be, say, in 10 years from now, we would probably need something interesting. It's interesting to think afresh on that question. One wish to have all cells of the same area. That's the basic thing. We thought at the time the cube will be easier to start with, so much of the thing I will present now will be about the hexahedron, the cube. And cube project on the sphere with central projection could be easily drawn. But now, if you continue there, this is the gnomonic projection between the cube and the plane. This is a 1 minus 1 plus 1 square, and then the 1/6 of the surface here. Then you can draw regular mesh here. So we can compute easily. If you have your star here, it's very easy to assign a particular square to a position in the sky. And then what we would like to have is to start on that and to back project here with an equal area projection, not a central projection, so that the boundary here on the spherical square, the edge, are the images of the edge of the first square. So this is just what is common between the central projection and the equal area projection. Inside, it's different. So let's see how it could work ideally. This is one of the results, a face which is back projected by some equal area, the one I will describe later. So imagine you have a square here with few stars. I mean, by projection, it projects here. This one will project at the same symmetry place, and what is important is that the two have the same areas, which is impossible if you take just central projection. So what we did, it was in 2002. On June 27, I don't remember when we starting, that was spring, May, March, can't remember. But anyway, we have two notes, one by Michel on the 27 June of 2002, pavage hiérarchique de la sphère, it provides an answer of that. And then I have mine, next day. So I don't remember how we work in parallel and so on. It doesn't matter. But clearly my introduction leaves no doubt about the fact he found the solution before. Michel, voici mes premières remarques, compléments sur le pavage de la sphère. Je te propose une dérivation générale de ta projection, and so on. So we are working almost next door. Our office is in the same hallway, and we meet very often. So if you look at his introduction, it's very clear. I mean, I like this synthesis. It's exactly the main item we would like to fulfill in this derivation. The pavage must be hierarchical, meaning each cell could be subdivided again in similar cell. The tiling should be as simple and regular as possible. For a given level of depth, the surface should be all more or less equal. And the shape of the cell would be also very simple. So it's very loosely defined. Obviously, it's some attempt to do something which looks like beautiful at the same time. Not only useful, but beautiful. Well, the math of that, which is essentially my derivation. So one starts from the spherical square on the sphere. Okay, that's fine. And this spherical sphere must be back projected on an equal area projection on a unit square, and reciprocally, obviously. So this is what we have. We are looking for two functions, x and y, from the spherical coordinate on the sphere, so that we have the symmetry. First, essentially, we would like the red line being image of the red line on the right, horizontal and vertical, exactly, so that we can, after that, reproduce the same plotting on the 5 other sides of the faces. Boundary is a square, and then area preserving. Essentially, we would like to satisfy this, which is not satisfied by the central projection. So if you develop this in detail, the two edges plus or minus 1 are projected on the line which are great circle alpha. The upper edge are also projected on arc of great circle. And then this push now we have to simplify because there are infinitely many solutions in practice with that. So we simplify, we say probably the first function should be just a function of right ascension, longitude. And then you take the area preserving condition, which gives some differential equation, which can be solved. We add also that the image of the upper edge also must be identical to that of central projection, which means the function g is constant over plus or minus pi over 4 on this, not pi over 4, on the great circle particular. Yeah. Oh, okay. Yes, this is what I've done. So, don't go into the detail. It's not a very complicated computation once you have designed it, and you have the direct projection from the sphere to the plane, and the inverse projection from the plane to the sphere. You can see when x is plus or minus 1, this is the same as alpha plus or minus p over 4, and the same on the other side when you are along the line of the top of the bottom of the square. So at least we have some number, some result. So let's look and make the comparison between the central projection and this equal area projection, which I've denoted, for lack of better name, Henri Mignard at the moment, but it's not very modest. I will find a name which is more neutral sometime. So at the left, you have the central projection with order 2, so 4 internal square, and the same order on the right. You can see immediately near the edge that the shape is less distorted, and then the surface, it's not easy to see because there is another projection here to present it on a 2-dimension. Okay, but all the surfaces here are identical. The surfaces here are not identical. They are larger that are close to the edges. Same with, I don't remember, 16 or 32. Again, you can see the almost uniform size. It's not completely obvious on the plot, but it's definitely not valid here. That's clear. And then for the beauty, not this one? Okay. Okay, comparing, to show you the comparison, this is central projection, and superimpose the area, not yet superimpose, equal area projection, and then superimpose. I mean, the blue one is the central one, the purple one is the equal area. You see, you don't divide exactly the same. But at least it provides a solution which gives you equal area, so it's perfect for storing information and retrieving information, computing density, computing integral by replacing by sum, and so on and so on. And then a very, very big one, the biggest I could do, and which is still readable. Yes, it's not, it's a bit tiring for the eye, but it's a nice one. We can do something else, obviously, since we have a projection now, which works tile by tile. We can imagine a globe of cubic form, which has been done in the 16th century with central projection. But this one is with equal area. And since we work tile by tile, we can explore 2, 3, the 9 available net for a cube to generate a cube, which I did actually. And this was presented to Michel for his scientific jubilee in 2007, I think, at the observatory. That's an example of projection here in a cube, unmade, very simple, but still it's interesting to see that. Obviously, it's difficult to see the difference in a country between central and equal projection, but in practice, it is a difference. So, some side development and further current activity. Something I did more recently, which I'm sure would have pleased Michel. In doing the program, you may imagine I have to explore all the face. For a cube, it's not too difficult, but since my plan is to do that for the octahedron, the icosahedron, I have to find a systematic way to go from one face to another one, to copy what I did in the main face to the other one. So to apply 19 rotations, so that to explore only once each of the other faces, which is not completely trivial to find the axis of rotation and then the succession of rotation. So this is the example. This is kind of plot which takes about half a day last week to design. Why I put that? Because you will see there is an interesting connection between the dual polyhedron, between the cube and the octahedron here, when you want to do that for the cube. So what is the issue? You want to explore in a loop, do for something like 1 to 8, 1 to 6 for the cube, and be sure that at each part of the loop you explore a new face we have not seen before. So the projection from our plane is generated one time, and then by a rotation, copy at the different faces. So the question is how to generate the face into section only once. So with the cube, it's very easy. You take that, I have on my desk, and then you rotate yourself, you see, okay, it's easy. When it's come to the icosahedron, it's much more difficult to visualize and to be sure you are doing that properly. So I wanted to have something more or less automatic, generating the right rotation. So for the cube, it's easy because you associate the octahedron, which is the vertices are the face of the cube. So going through the vertices of an octahedron is exactly the same as going through the faces of the cube. So the octahedron is the example given here with a face, can be projected in its planar graph. And what it means, exploring the face of the cube is generating an Hamiltonian path of this graph, which is quite easy to do in practice. Path or cycle. We need a path, we don't need a cycle. So cycle is perfect, but path is sufficient for that. So any Hamiltonian path on this graph provide an answer. So this can be generalized to the icosahedron. So the dual polyhedron is the octahedron, which can be projected on a planar graph. So you see a few number of put there corresponding to this edge here, and which correspond to specific face, the same number here. And then, okay, you know normally how to generate Hamiltonian paths on any graph of a regular polyhedron, and then you know how to put that in the program to explore all the faces of the icosahedron. This is one of the things. The current work, on which I'm still working on that from time to time. It's something which is in the background. So what I've done is essentially projecting from the central projection a square, unit square, to the sphere, and then design an equal area projection which get back to the same square boundary, but not the same square inside limits, inside square. So you can do directly with a mapping, making the correspondence from the initial square to the final one without using the sphere, which makes using say, Cartesian coordinates, which are normally much better than angular coordinates. So the question will be a transformation from eta zeta here to xy there, fulfilling the area condition, which is not 1, because the initial projection here must recover the distortion from the central projection. And then this is an example from how projection it gives this. So if you look at that now, it will explain why I'm not fully happy with that solution. It's a solution. It's okay. It works and so on. But if you look now from this perspective of mapping from one square to another one, you would like to preserve the symmetry of the square, meaning eta, zeta, xy are more or less interchangeable. So we would like to have some symmetry in the formula. So if you look at that projection, definitely eta and zeta does not play the same role. So it means we have lost some symmetry in the process, which is not there, not easily visible in the mapping, but definitely if you rotate an image by 90 degrees, it's not exactly the same as the initial one. So it would be nice to have something fully symmetric. So what is desirable is a transformation of this kind that we have here, fulfilling this area. In total, it's not fully equal area, it's area condition. And then, so that the y of zeta eta should be the same as x of eta zeta. This is not completely trivial. At the moment, I have not found a right solution. And then it leads to, this is okay in our transformation. This is not okay at the moment. It's not symmetrical, which is not very pleasant. So where is the lack of symmetry? This is our projection. The blue lines are actually great circle arc within the square, which is not the case for the yellow line. They are not great circle. So it will be desirable to improve that. And then one solution could be from the start, instead of using the astronomical, in some sense, spherical coordinate with origins come from the fact the Earth is rotating, and astronomers have been very happy to use right ascension. But if you do geometry and want to keep the symmetry, it will be much better to use a new coordinate system. The first one will be the same as usual, the longitude around z-axis, but you could define a beta, which is a longitude around y-axis. This is a perfectly admittable map in terms of differential geometry for the sphere. It has the defect that the local frame is not orthogonal, but at least you can compute the metric and the area in terms of that, which is completely symmetric. My guess at the moment is that it's probably impossible to combine both. Equal area projection, I have not a full proof, but have an hint now that shows that it's probably not possible to have a full symmetry in the two directions, meaning the line would be great circle arc in that direction, great circle arc in that direction, and a small square would be all the same area. This is, for me, an open question I have not solved yet, but I'm still thinking of that. I'm thinking you would have liked. Well, I took this picture of Michel in his office. I say it's two offices of mine, because if you can see in his office here, there is a small cube. It was on his shelves for a certain number of years. And then, I don't know for which situation, someone brought it to me when his office was given to someone else this year, obviously. So this is, they are now in my office. Thank you very much.
Thank you very much. Question? So, solution? No, so thank you again.